In the previous lecture, we have started with the function of complex variable. So we have seen that z is equal to x plus iy is a complex variable, and then we have defined a function f of z, which is a function of complex variable z, and we have also seen that this function f of z is again a complex. Okay, so we have defined the limit of the function. We have defined the continuity of the function. We have defined the differentiability of the function. And using differentiability, we have defined that the analytic function. Okay, so let us see what is the analytic function we have. Okay, so we have defined analytic function. So what is the analytic function we have? The function f of z is equal to u plus iv is said to be analytic if it is differentiable at every point in the given bounded region R or is P. Okay. So the function f of z is said to be analytic if it is differentiable at every point in the given bounded region or the disk. Then we have seen what are the necessary and sufficient conditions. So what are the necessary and sufficient condition for a function to be analytic? So let f of z is equal to u plus iv be a function of complex variable z, then the necessary and sufficient conditions for f of z to be analytic are, so what we have, the first condition w by x is equal to w by y, and w by y is equal to minus w by x. So that is, these are called CR equations. These are CR equations, Cauchy-Riemann equations, and we have the second condition that w by x, w by y, w by x, and w by y are continuous. Okay, so these are the necessary and sufficient conditions for a function to be analytic. Okay, now using these conditions, we are able to test whether the function is going to be analytic, so without finding its derivative. But can we find the derivative using this condition? The answer is yes. Okay, so what we can have is, if f of z is equal to u plus iv is an analytic function, then what we have is f dash of z is equal to ux plus ibx. So you have ux plus ibx. That's what we have. Or then we can, using this CR equations, we can write all the different four forms of this f dash of z. Okay. So now uh, our task is to find whether the function is analytic or not. And so if I want to test whether the function is analytic or not, then what we have to do is first we should know u and v. So first we have to separate the real and imaginary part of the function. And once you have the real and imaginary part of the function, then second step is to find out this derivatives and test whether these two conditions are satisfied or not. And if these two conditions are satisfied, then we can say the function is going to be analytic function. Okay. And if these conditions are not satisfied, then we say the function is not an analytic function. And if it is asked to find the derivative, then this will be the third steps. Okay. So this will be the third step. Now we have to solve the problem. So let us see the problem. Okay. What we can write is do that f of z is equal to z square is an analytic function, and hence find f dash of z in terms of z. So here we have to find this f dash of z also. So remember the three steps. First, we have to separate the real and imaginary part. Second, we have to test the necessary and sufficient condition. And third, we have to find the derivative of f in terms of z. Okay, so these are the three steps that we have to follow. So let us see the solution. So what will be having? Let f of z is equal to z square be the function of complex variable z. Okay. So if I want to separate the real part and imaginary part, then I have to put z is equal to x plus iy. Then if I put z is equal to x plus iy, what you will get is f of z is equal to x plus iy bracket square. So it is going to be x square plus 2x iy plus iy bracket square. So a plus b bracket square is going to be a square plus 2ab plus b square. So we can write this as, okay, what we have here. So this is going to be x square plus 2ixy and plus I square y square. So what we know is, since I square is equal to -1, we can write this as x square plus 2ixy minus y square. Or we can simplify this as, so I'll be having f of z is equal to x square minus y square plus I times 2xy. As we have to separate the real and imaginary part, so I have taken all the terms without I and the terms with I. So we can write here, hence f of z is equal to u plus ib, okay, where you have u is equal to x square minus y square and v is equal to 2xy. So here we have completed the first step to know what is u and what is v. And now we have to consider the second step. So in second step, what we have to do is we have to find the derivative and then test the condition. Okay, so let us find the derivative and then test the conditions. So consider, Okay, what you have w by wx is equal to 2x w by y is equal to minus 2y. And what we'll have w by wx is equal to 2y and w by y is equal to 2x. So when we are finding the derivative, partial derivative, then the other variable is treated as a constant. So when I am finding the derivative of u with respect to x, so y is treated as a constant and hence the derivative of y is going to be 0. So similarly for derivative with respect to y, again, so when we are finding the derivative with respect to y, x is treated as a constant and hence the derivative of x with respect to y is going to be 0. So the derivative of y square is going to be 2y and this minus sign remains here. Now, what we have here, the same thing we have to do for this v also. The derivative with respect to x, 2y is treated as constant. The derivative with respect to y, 2x is treated as a constant. Okay, and hence we have this term. Okay, now we get. So you can see this term and this term, they are exactly same, and this term is minus of this term. So we get w by wx is equal to w by y, and what we get is w by y is equal to minus times w by wx. Can you see what we got actually? So you can have here. So exactly the CR equations we have obtained and they are satisfied. Okay. So what we can say is this equation is one of the CR equation. This is the next CR equation, and hence what we can say is that is Cauchy-Riemann equations. As I said, you can use abbreviation. So Cauchy-Riemann equations are satisfied. Okay, so these equations are satisfied. But we know that though these equations are satisfied, but these equations does not guarantee the function to be analytic. So we have to be careful for this equation, and hence if it doesn't guarantee the analytic nature of the function, so we have to go for the sufficient condition. So this is necessary but not sufficient, and hence what is the sufficient condition we have? We have to check the continuity of these functions. So now you tell me whether these functions are continuous or no. Now it's your turn. Tell me whether these functions are continuous or not. Continuous. Okay. 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 So tell me the justification why you think that it is continuous. What is the justification that why you are yes? Akhilesh has given. Good. Abhinav has also given. Correct. So you got it. That's good. Very good, Dipesh. Okay. These are polynomial functions. Okay. So these are going to be the polynomial functions. There is a polynomial, this polynomial, and we know the polynomial functions are going to be continuous function. As we know, it is one of the Lie functions, so it is going to be continuous. And hence, you don't have to show the continuity, but you have to identify. So we can say, since w by wx, w by y, w by wx, and w by y are continuous. Okay. Hence, the necessary and sufficient conditions are satisfied. So you got the necessary and sufficient conditions satisfied, and hence you can say f of z is an analytic function. So f of z is going to be an analytic function. Okay. So we proved that the necessary and sufficient conditions are satisfied, and hence the function is going to be an analytic function. So that was our second step. Now third step is to find what is going to be f dash of z in terms of z. Okay. So what we know formula for finding the derivative. Okay. So what we can do is to find f dash of z, we have what you can say is f dash of z is equal to ux plus ibx, and what you'll be having, this is 2x. Okay, so 2x plus I 2y. So we can have 2 common, and you'll be having x plus iy. Since what we know is x plus iy is equal to z, so I can write this as 2z. Okay, so what we got here, hence we got f dash of z is equal to 2z. So this is how we are able to get the derivative of this function f of z is equal to z square. See here, we were having the function f of z is equal to z square, and then we proved that it is going to be an analytic function using the CR equation and necessary and sufficient condition, and then using the formula for f dash of z, we calculated the derivative. Okay, so we calculated the derivative f dash of z, and we proved that it is going to be 2z. So please be careful while writing 2 and z. So that's why always write this 2 and z. So we have to be careful. Okay. Now, do you have any doubt in this example? Is there any doubt in this example? Okay, that's good. Don't have any doubt. So it's a easy and straightforward question. So let's try the another question. Okay, it's great. Okay, so we go with the another question. Okay, so we can have show that f of z is equal to hyperbolic sine z is an analytic function, and hence find f dash of z in terms of z. Okay, so that's what we have to find. Okay. Now here what we have is let f of z is equal to sine hyperbolic z be the function of complex variable z. So we want to find the real and imaginary part. We have to separate here, and hence what we do is put z is equal to x plus iy. We get what you have, f of z is equal to hyperbolic sine of x plus iy. What we know, hyperbolic sine of a plus b is equal to hyperbolic sine of a into hyperbolic cos of b plus hyperbolic cos of a into hyperbolic sine of b. Okay, and then what we know is since hyperbolic cos of ix is equal to cos x and hyperbolic sine of x, hyperbolic sine of ix is equal to I times sine of x. So these are the relations between the trigonometric function and the hyperbolic functions. So we have to simplify in that using these formulas. So let us simplify. So I'll get here f of z is equal to, this is hyperbolic sine x into hyperbolic cos of iy plus hyperbolic cos of x into hyperbolic sine of iy. Okay, so using this formula we simplified this. Now use this too, and then we have, this is hyperbolic sine x cos y plus I hyperbolic cos x and sine y. So that's what we got, f of z. Okay, and hence I can write this as f of z is equal to u plus iv, where u is equal to hyperbolic sine x cos y and v is equal to hyperbolic cos x and sine y. Okay, so now once you get u and v, so we have completed the step 1, that we got the real part and we got the imaginary part. Now we have to think of the second step. Okay, so we have consider w by wx. Okay, so what is going to be w by wx? See, the derivative we have to calculate, and then what we know about the derivative of hyperbolic function. So d by dx of hyperbolic cos x is equal to sine hyperbolic x, and the derivative of hyperbolic sine x is equal to hyperbolic cos x. So here we don't have the negative sign, so it is in the trigonometric ratios only, or trigonometric functions only. So with respect to x, we have, this is cos hyperbolic x into cos y, and w by y is equal to minus sine hyperbolic x, and this is sine y. So sine hyperbolic remains as it is. The derivative of cosine is minus sine, so we have, this is minus sine. Okay, and now we have to find the derivative of this term. So w by wx. So we'll be having, this is sine hyperbolic x to sine y, and w by y. So we got, this is cos hyperbolic x and cos y. Now what we can have is, see, this term is exactly same as this term, and this term is going to be negative of this term. So what we can say is, we have w by wx is equal to w by y, and we got w by y is equal to minus w by wx. So here we got these two equations, and as you can see, these are nothing but the CR equations. Okay, so these are exactly the CR equations we got, and hence once we get CR equations, so we can say that is CR equations are satisfied. So we have here, that is CR equations are satisfied. Okay, but as we know, only CR equations are not sufficient. Okay, so this is necessity, but not sufficient. Now we have to think of the sufficiency. What we can say about these functions? So these functions, are they continuous? Okay, so that's what we have to think. Now we know trigonometric functions are going to be continuous function, whereas the hyperbolic functions, So hyperbolic functions are actually the algebraic sum of exponential functions. And we know the exponentials are continuous. So the exponential functions are continuous, the trigonometric functions are continuous, and we know if the two functions are continuous, their product will be also continuous. And hence, this is the product of two continuous functions, so continuous, and so on. This is a continuous function. So if this is continuous and this is continuous, these two are exactly same as these two. So we can say all these are going to be continuous. And when you say these are continuous, the sufficient conditions are satisfied. So we can say since dabba u by dabba x, dabba b by dabba y, dabba u by dabba y, and dabba b by dabba x are continuous. Okay, so these are continuous, and hence the necessary and sufficient conditions are satisfied. The necessary and sufficient conditions are satisfied, and hence we can say the function, we can say f of z is an analytic function. So we can say f of z is going to be an analytic function. Now see, our first step was to find real and imaginary part of this function that we have calculated. So we completed. Second step was to test whether this function is going to be analytic or not, and that also we have completed. Now we have to think of the third step. So we have to find f dash of z in terms of z using this whatever we have calculated. Okay. So now we have f dash of z is equal to ux plus ivx. So what is ux we have got? Okay. So you can see it is cos hyperbolic x cos y plus we have sin hyperbolic x and sin. Okay. So you can see ux plus ivx. So ux plus ivx. So we got here. Okay. Then we have to simplify this. So what we got here? We got f dash of z is equal to cos hyperbolic x cos y plus I sin hyperbolic x and sin y. So what we know is since cos hyperbolic ix is equal to cos x and sin hyperbolic ix is equal to I sin x. Okay. So using these two formulas, I can write this as cos hyperbolic x into cos hyperbolic iy plus sin hyperbolic x, and this I sin I can write as sin of iy. Okay. Now we have the formula. So cos hyperbolic a to cos hyperbolic b plus sin hyperbolic a into sin hyperbolic b is equal to cos hyperbolic a plus b. Okay, so this formula we have seen in same one. So if I use this formula, what I'll be having? This is cos hyperbolic x plus iy. But what we know is since x plus iy is equal to z, so I can write this is cos hyperbolic. Here we got this as, so we got that f dash of z is equal to cos hyperbolic. So So this way we are able to find the derivative of the function, given function, in terms of. Now you can observe one thing. Okay, see in the previous example, the derivative of z square we obtained 2z. Okay, the derivative of sine hyperbolic z we obtain cos hyperbolic z, which is very similar in case of real variables. So this is for the real variables, and we are getting very similar for the complex variable also. So most of the times, the real variable case and complex variable case will be similar. Okay, and that's why we can use the formulas of real case sometimes to have the case of complex variable. Okay, so this is how we are able to get the solution for this. Do you have any doubt in this problem? So if you have any doubt or any step you are not able to get, then please ask. So if you have any doubt, you are welcome. So I hope there is no doubt. That's good. Okay. Now let us try another example. Okay, so where you can see how the necessary and sufficient condition work. Okay. So we have an example. Okay, show that the function of z is equal to x cube y raised to 5 x plus iy upon x 6 plus y raised to 10 if z is not equal to 0 and is equal to 0 if z is equal to 0. So this is going to be z. So this function is a continuous function. Okay, so if you put z is equal to 0, it is going to be the function value, which is same as the limiting value. So we can say f of z is going to be continuous function. So we have to show that this function is not analytic. So CR equations are satisfied at z is equal to 0. Okay, so here we have to show that this function is not an analytic function, so it satisfies CR equation. So that's why this example will give you the idea why these conditions, CR equations, are not sufficient. Yeah, they are necessary, but not sufficient. Okay, so here we'll go with the solution. So what we'll be having, right? F of z is equal to x cube y raised to 5 into x plus iy upon x raised to 6 plus y raised to 10. Okay, or z not equal to 0 and this is equal to 0 or z is equal to 0. So that is we have f at 0. Okay, so f at 0 is equal to. And now if I want to test CR equation, that means I should know what is going to be u and what is going to be v. Okay, so first we have to separate what is u and v. Okay, so v and z. the function of x variable z. Okay, so to separate, we have to separate this real and imaginary part, and hence we have f of z equal to x cube y raised to 5 x plus iy on x raised to 6 plus y raised to 10. So I can write this as x raised to 4 y raised to 5 plus I x cube y raised to 6 on x raised to 6 plus y raised to 10. Okay. Now we can have this as x raised to 4 y raised to 5 x raised to 6 plus y raised to 10 plus I x cube y raised to 6 on x raised to 6 plus y raised to 10. So this is f of z, and hence we can say f of z is equal to u plus iv, where u is equal to x raised to 4 y raised to 5 on x raised to 6 plus y raised to 10, and v is equal to x cube y raised to 6 on x raised to 6 y raised to 10. So that's what we got. Okay. Now we have this is the first step that we have completed. Now we have to think of finding the derivative of these terms. Okay, so what we know for the derivative of u upon v is equal to v as it is, derivative of u minus u derivative of v upon v square. Okay, so this is the rule for derivative of u upon v. Now this is the function of x, this is the function of x, and so we have to use that rule. So this is the function of y, this is also function of y, so we'll use that rule. And hence, now we consider w by x. So let us consider, then you will be having x raised to 6 plus y raised to 10 into 4x cube y raised to 5 minus x raised to 4 y raised to 5 into 6 x raised to 5, and upon we have x raised to 6 plus y raised to 10 bracket square. Then you will be having w by y. So it is x raised to 6 y raised to 10. You got here, this is y we are finding with respect to now. So we'll be having 5 x raised to 4 y raised to 4 minus x raised to 4 y raised to 5, and this is you will be having 10 y raised to 9. Okay, and here we get x raised to 6 plus y raised to 10 bracket square. So we got the derivative of u. Now we have to think the derivative of v. Okay, so we can have hence above v by above x. So you got here x raised to 6 plus y raised to 10 into 3x square y raised to 6 plus x cube y raised to 6 to 6 x raised to 5 upon we have x raised to 6 plus y raised to 10 bracket square. And next we have to find out with respect to y. So let us find out with respect to y. So we can have w by y. So this is x raised to 6 plus y raised to 10. Then here we got 6 x cube y raised to 5 plus x cube y raised to 6 into 10 y raised to 9 upon we have x raised to 6 y raised to 10 bracket square. Okay, so these are the derivatives you are able to calculate, Okay. Now see the question properly. Okay. So what is given that? Okay. See, we have to show that the function is not analytic at though it satisfies CR equation at z is equal to 0. So what we have to consider? Everything we have to consider at z is equal to 0. Okay. So what is mean at z is equal to 0? So what will happen at z is equal to 0? Okay. So we get at z is equal to 0. So that is when you say z is equal to 0, it is obvious that its real part is 0 and imaginary part is 0. So at z is equal to 0, what will happen? We get w by w x, w by w y, w by w x, and w by w y. Okay, so this way every term, every derivative will turn out to be 0 at 0, and hence we can say easily that CR equation are satisfied. So that is, or we can say we have w by wx equal to wb by wy, and w by wy is equal to minus wb by wx. So this way we are able to get the CR equations. So we can say that is CR equations are satisfied. Okay, so we got CR equation satisfied. Now we have to test the continuity of this. Okay, so the question is, what will be the continuity? Are we able to test the continuity of this? Okay. So what do you think? Whether this will we are able to test the continuity, or will this function will be continuous? Will this function be continuous? So whatever the functions we have, w by wx is equal to 0, w by wy is equal to 0, w by wx is equal to 0, and w by wy is equal to 0. So these are the first order derivatives we have. So do you think that these functions will be continuous? The question is why not? Okay, so if you say they are not continuous, then the question is why? Good. So yesterday I told you that this functions, okay, light functions will be continuous. Okay, apart from light function, there is a point function which is not continuous, and hence here these are all point function, so not continuous. We cannot test the continuity of this. Okay, so that's good. Remember. Okay. These functions here, whatever we have obtained, are the point functions, and hence these functions are not going to be continuous. Okay, so what we can say is the sufficient condition which is required here is not satisfied. So this is the CR equations are satisfied, but we are not able to check the continuity here. Okay, because of the point function, and hence we cannot guarantee that the function is analytic. Okay. Now, the other way to check whether this function is analytic or not, we know this function is going to be continuous. Okay. So, if this function is continuous, the question is it differentiable? Okay. So, if it is differentiable, then our work is done. But then, if it is not differentiable, then we can say it is not analytic. So, let us check whether the derivative exists or not. Okay. So, Now we consider. So what is the formula to check the derivative? So first formula or first principle, limit z tends to 0. At 0 we have to consider. So what will be having f of z minus f of 0 upon z minus 0. So that's what we have. Limit z tends to 0, x cube y raised to 5 x plus iy upon x raised to 6 y raised to 10 minus 0 upon, I can write this z as x plus iy, and minus 0. So we can simplify this. Limit z tends to 0, x raised to 5 x cube y raised to 5 upon x raised to 6 plus y raised to 10. So we have here y raised to 10. Okay. Now you can see that this x plus iy and this x plus iy will get cancelled. So here, what this limit is, okay, so we try to simplify. So what I can say is, since z is going to be 0, then what it means? It means that x is going to be 0 and y is also going to be 0. So we get, what you are able to get is, we are finding limit z tends to 0. F of z minus f at 0 upon z minus 0. And this we got limit x tends to 0, y tends to 0. So here we have x cube y raised to 5 on x raised to 6 plus y raised to 10. So now this is the limit that we have to calculate. Okay, and so here x has to go to 0, y has to go to 0. This both has to go to 0 simultaneously, and so we call this as a simultaneous limit also. Okay, or this kind of limits are also called as simultaneous limit. So which is a part of multivariate calculus. Okay. Now what we have to find out the solution for this limit. So what we know is limit x tends to 0, y tends to 0. So we have here x cube and y raised to 5. And in the denominator, we have x cube square y raised to 5 square. Okay, so if you are able to identify this, then it is very easy. So now, what we can say is, see, we have the terms x cube and y raised to 5. And you can see in the denominator also we can see the same terms x cube and y raised to 5. So that means there is some relation for this simultaneous limit, so that this will happen simultaneously and this will reduce. So what I can say is, either I can say x cube is equal to m y raised to 5 or m x cube is equal to y raised to 5. So either of this. So either x cube is m y raised to 5 or m x cube is y raised to 5. So if I use any one of this, okay, then as x tends to 0, obviously y will tends to 0. If y goes 0, obviously x will go to 0, where m is some constant. Okay, and so we can use any one of this, and hence we can say, okay, so what will be having? Put x cube is equal to m y raised to 5. You can use any one of this, that doesn't matter. Okay, then as x tends to 0 implies that y will go to 0. Okay, so that's why I restrict you to use this symbol. So this symbol means implies when x will go to 0, then by this equation y will go to 0. And hence what we are able to get is, we are finding this limit. So we have, what will get? Limit z tends to 0. F of z minus f at 0 on z minus 0. This is what we are finding. So limit, now x we have replaced by y. So only y will tends to 0. As x tends to 0, y will go to 0. So this is m y raised to 5 and y raised to 5. Here we have m y raised to 5 square plus 12 having y raised to 10. So I can write this as limit y tends to 0, m y raised to 10, m square y raised to 10 plus y raised to 10. So you can see easily that we can take y raised to 10 common. So limit y tends to 0, y raised to 10 into m upon y raised to 10, and we have 1 plus m square. So we can write this as limit y tends to 0, m upon 1 plus m square. Or we can write that limit z tends to 0, f of z minus f at 0 on z minus 0 is equal to, here now you can see there is no y, so this will not, this term will not affect, and hence you can write m upon 1 plus m square. So it is m upon 1 plus m square. Now the question is, what is the value? Okay, so you can see that the basic theorem of limit is independent of path. Okay, but here this limits depends on path. So this limits depends on the value of m, and hence we say it does not exist. Because if you put m is equal to 1, you will have half. You put m is equal to 2, you will have 2 by 5, and so on. For the different value of m, you will have the different value of this limit, and hence we say this limit does not exist. So we can write here, since the above limit depends on path, that is the value of m, and hence the above limit does not exist. So what we were calculating, actually we were calculating the derivative. So that is what we can say is f dash of z does not exist at z is equal to 0. So we can say f of z is not analytic. So this is not analytic at z is equal to. Okay, so this way we are able to prove that. So having only the CR equations is not sufficient. So in this example, we proved that CR equations are satisfied, but this function is not differentiable. So if the function is not differentiable at a point, then we cannot say it is going to be analytic. Okay, and hence through this example, we proved that the CR equations are not sufficient conditions.